Hello everyone, and welcome to another video with Special Maths Academy. In this video, we'll be discussing the 12th problem from the Special Maths contest. And it says, 2024, round one, yeah. And it says, let M and N be members of the set of integers. Let A be the GCD of, M to the power of 5 and N to the power of 5 plus 1. And let B be the GCD of M to the power of 5 plus 1 and N to the power of 5. And let C be the GCD of n to the power of 10 minus n to the power of 5 minus 1, and n to the power of 10 minus m to the power of 5 minus 1, and m times n all to the power of 5. And let D be the GCD of m to the power of 10 plus m to the power of 5, and n to the power of 10 plus n to the power of 5. Then we have, okay, so we want to look at these statements and check which of them is correct. So it's enough to find one counter example. Okay, so but before I move on, I'll just define what GCD is. So GCD is the greatest common divisor. An LCM, okay, so I'm just defining LCM because we'll use it eventually, is the lowest common multiple. Okay. So for the first one, let's see if we can find the counter example. So if I set Mn to be equal to 2 and 3. What do we have? So let's evaluate what A is. So we have A is equals to a GCD of 2 to the power of 5. So here it's going to be 32. And 3 to the power of 5 plus 1 is 243 plus 1, so 244. And this is 4. Okay. And B is going to be equal to the GCD of 2 to the power of 5 plus 1, that'll be 33. And 3 to the power of 5 is 243. So GCD here is 3. Okay. So the mean of AB is equal to 3. Okay, so 4 and 3, the minimum is 3. So we see that option A is wrong. So let's look at option B. Option B, we have C is equals to 1. So what counter example can we find? So if we consider M and N to be 1, 2, and then let's evaluate this. Okay. So the GCD of C is equals to the GCD of, so 1 to the power of 10 is 1, minus 2 to the power of 5 is 32, minus 1, and then we have 2 to the power of 10 is 1024, minus 2 to the power, minus 1 to the power of 5, minus 1, minus 1. Now we have m times n all to the power of 5, that is 2 all to the power of 5 is 32. So this is equals to the GCD of, so 1 minus 32 minus 1 minus 32, 1024 minus 1 minus 1, 1022, and then we have 32. So this is equals to 2. Okay, so we can see that C is not equals to 1 here. So C equals to 2, not equals to 1. So B has an issue. Now let's look at option C. So option C, we can set M and N to be equals to 1, 2 again. So here, let's just evaluate D and see what we get for the value of D. So we have D is equals to the GCD of M to the power of 10. So 1 to the power of 10 plus 1 to the power of 5 is 1. 2 to the power of 10, 1024, plus 2 to the power of 5 is 32. So this is equals to the GCD of 2 and 1056 is equals to 2. Okay. So we have C is equals to D here. So C is not greater than D. Okay. So you see that option C is wrong. So let's look at option E. Option E, we set M and N to be 1. 1, 1. So let's evaluate option E. So let me erase this. So look at option E, set M and N to be 1, we have A is equals to the GCD of, so 1 to the power of 5 is 1, 1 to the power of 5 is 1 plus 1, 2 is equals to 1. Then we set B equals to the GCD of, so 1 to the power of 5 is 1 plus 1, 2, and then 1 to the power of 5 is 1, so this is 1. And then we said that we can see that D is going to be equal to the GCD of 1 to the power of 10, it's 1 plus 1, 2, 1 to the power of 10 is 1 plus 1 to the power of 5 is 2. So this is the GCD of 2 and 2, which is 2. So we see that 1 times 1 is not equals to 2. Okay, so this option A is wrong. Now, in an exam at this point, would be happy because we can just move on and consider that our job is done. But for the sake of this video, let's try and see if we can, prove that the fourth statement is always true. Okay. So I will just put something here. Say so properties of so I'll just put properties of GCD and LCM that I'll be using. So I'll state a property before I use it or as I'm using it. And those who are interested in further studies, can check it out. Okay. So the first thing I want to show is that the GCD of A and B is equals to 1. Okay, so let's see how I can show that. So the first property I'll write is that, so property I, so we have the GCD of, let me use X and Y. So GCD of X and Y. So the GCD of X and Y divides X, and of course, GCD of X and Y also divides Y. So this vertical stroke means divides, okay? Not sure that is equals to 1. And then this another property I'll be using is that, so let's say we have the GCD of X and Y is equal to Z. Then D divides X and D divides Y. So if and only if D divides Z. Okay. So now let's look at this. Okay, and then the third property. Okay, so yeah, properties are quite a lot. So if we have the GCD of X and Y being equal to Z, okay, so we have that Z divides X and Z divides Y. So now from the first statement, we have that A is equal to the GCD of M to the power of 5 and N to the power of 5. So of course, we're talking on greatest common divisor. So A divides M to the power of 5. So we can just, let's just use this. A divides N to the power of 5. And we can say that B is the GCD of M to the power of 5 plus 1 and N to the power of 5. So we can say G divides M to the power of 5 plus 1. Okay. So now we know that the GCD of, okay, A and B, so it divides A, and the GCD of A and B divides B, okay? But A divides M to the power of 5, and B divides M to the power of 5 plus 1. Okay. So where am I driving at? So this implies the GCD of A and B divides M to the power of 5, and the GCD of A and B divides M to the power of 5 plus 1. Okay, so for this line here, so I kind of used a property of division. So if we have that A divides B and B divides C, then we'll have that A divides C. Okay, so I use that here. Then also coupled with the fact that I use property 1. So the GCD of A and B divides A, GCD of A and B divides B. Okay. So now, then we can then look at property. We can look at property 2. Okay, so the GCD of A and B divides these two things. So it means the GCD of A and B must divide the GCD of, okay, so m to the power of 5 and n to the power of 5 plus 1. Okay, but now GCD of two consecutive integers is 1. Okay, so GCD of A and B divides 1 basically. So it implies that the GCD of A and B must be equals to 1. Okay, so I've proven this first statement I wanted to show. Okay, so I'll just erase it. You can always pause the video to, convince yourself more. So I'll erase it so that I have more space. The next thing I want to show is that A divides C and B divides C rather. Okay, so let's see how we can, prove this. So this second property, you can extend it to, more values basically. So most of these properties I'm stating here, you can extend them to like GCD of 3 values and so on and so forth. So let's look at this. So basically this second property can make it 3. So I think I will just let me scroll down a bit. So I'll just write it here. So second property, but I'll write it in for the version of 3. So let's say W X Y equals to Z. Then we have that D divides W, D divides X, and D divides Y. So if and only if D divides Z. Okay, so let's use that here. So let's look at this. So we have A divides m to the power of 5. So we have A divides m to the power of 5 and A divides n to the power of 5 plus 1. Okay. So we can kind of combine these two. So basically, this implies A will divide, so we can just do m to the power of 5 times n to the power of 5, of course, and then minus n to the power of 5 minus 1. Okay, so basically A will divide m to the power of 10 minus n to the power of 5 minus 1. Okay. Then for the second value in that GCD term for C, we can see that A divides n to the power of 5. So we can say A divides n to the power of 5 plus 1. So we're going to use some idea of difference of two squares. So n to the power of 5 minus 1. Okay. And then we know that A already divides m to the power of 5. So now when we evaluate this, we have that A divides, so that will become n to the power of 10 minus n to the power of 5 minus 1. Okay. And then we know that A divides m to the power of 5 already. So we have that A divides mn to the power of 5. Okay. So basically, A divides each of those three terms in the GCD expression for C. So it means that A must divide C. Okay. So when you combine all this, it means A must divide C. And analogously, you can prove the same for B. So I'm not going to, spell that out. So I'll just erase this. So you can always pause the video, convince yourself. Okay. Next property I'll use, so it's for LCM. So we have X divides Z and Y divides Z. Okay, so that implies LCM of X and Y divides Z. Okay. So we have A divides C and B divides C. So we have that LCM. So basically, you just follow. So we have that LCM of A and B divides C. Okay. Next property I will state. So this one, it's not very easy to generalize this to, multiple terms. So attention. So not all the properties here are easily generalized. So we have that GCD of X and Y. So let me just use X and Y so that it's distinguished from. So GCD of X and Y times LCM of X and Y is equal to X times Y. Okay, so basically, when we combine that here, we know that LCM LCM of A and B. Okay, so times the GCD of A and B is equals to AB, but GCD is equals to 1. So it means the LCM is equal to AB. Okay, so basically, we combine that to get this next thing, statement that AB divides C. Okay, so now we have AB divides C. So I want to try and get that C divides AB, and then if a number, if we have AB divides C and C divides AB, the only possibility is that AB is equals to C. Okay, so now I'm done proving that AB divides C. Okay, so let's go to the next step. So I'll scroll down a bit. So more properties. So I'll just put an asterisk here to show that the fifth property is not easily generalizable. Okay. So the next thing I want to show is that the GCD of m to the power of 5 and n to the power of 5 plus 1 is equal to the GCD. So recall that this is how A is defined basically. So let me put it here like this. So we have A equals to the GCD of m to the power of 5, n to the power of 5 plus 1. I'll show that this is equals to m to the power of 5, n to the power of 5, and n to the power of 5 plus 1. And I want to show that B is equals to, so this is how B is defined. I want to show that B is equals to, okay? So so these two statements are very analogous. So I'll just prove for one statement and the very similar argument hold for the next statement. Okay, so we have that, so basically the GCD of m to the power of 5, n to the power of 5, and n to the power of 5 plus 1. Okay, so it's equal to the GCD of, so can just, you can, reduce this, do some reduction. Okay, this is equals to, so I can simplify this. So n to the power of 5, n to the power of 5 minus n to the power of 5, n to the power of 5. So those two will cancel out. So we left with negative m to the power of 5, and then n to the power of 5 plus 1. Okay, so this is just this is just the division algorithm, the reduction. And GCDs are always positive values, so this is going to be same as, okay. So basically I've shown for the first one, and then the second one it follows. Okay, so that's it. Then let's go to the next statement. So for this statement, the property that I'm going to use is, so VI. So if you have that the GCD of X and V is equals to W, and you have that the GCD of x and y is equals to z, then that implies that the GCD of some of the statements are quite easy to prove, but I won't be proving them in this video, so the video is not very long. So that GCD of x and vy is equal to the GCD of wz. Okay, so we'll just apply that here immediately. So we can see that m to the power of 5, n to the power of 5 is repeated, here and here. So the next fact that we have is that, so a times b is equal to the GCD of, so I'll just put n to the power of 5, n to the power of 5, and m to the power of 5 plus 1 into n to the power of 5 plus 1. Okay, so I can simplify this further. So I have AB, so I'll just open the bracket. AB is equals to the GCD of m to the power of 5, n to the power of 5. So this will become m to the power of 5, n to the power of 5, plus m to the power of 5, plus n to the power of 5, plus 1. Okay, and this is equal to, so we have n to the power, mn to the power of, m to the power of 5, n to the power of 5. So we have it here. So it means I can just reduce that. So we have that AB is equal to the GCD of m to the power of 5, n to the power of 5, and m to the power of 5 plus n to the power of 5 plus 1. Okay? So the next statement is, so let's recall what C is. So C was defined as the GCD of m to the power of 10 minus n to the power of 5 minus 1, and then n to the power of 10 minus n to the power of 5 minus 1, and m to the power of 5, n to the power of 5. Okay, so let's just scroll up to confirm. So don't forget the value of C. Okay, so you can see that it's correct. So now, uh, what's what can we get from here? Okay, so basically we can do some bits of reduction. So we have that C divides. Okay, so let's just pick for instance, C divides m to the power of 10 minus n to the power of 5 minus 1. Okay, so this implies C divides, so we just multiply it by n to the power of 5. So we have m to the power of 10, n to the power of 5 minus n to the power of 10 minus n to the power of 5. Okay, so recall that C divides m to the power of 5, n to the power of 5. So basically, m to the power of 10 and times n to the power of 5 is the same as m to the power of 5 into m to the power of 5, n to the power of 5. Okay, so basically, this implies that C, so I'll just erase this. This implies that C divides negative n to the power of 10 minus n to the power of 5. Okay, so of course, negative values don't, count for anything. So this implies C divides n to the power of 10 plus n to the power of 5. Okay. Now we know that C divides this second value here. Okay, so we can now look at it this way. So C divides n to the power of 10 plus n to the power of 5. So from here, and then we bring this in. So minus n to the power of 10 minus m to the power of 5 minus 1. Okay, so we have that C divides what? So here, n to the power of 10 will cancel out with n to the power of 10. Then we have negative minus m to the power of 5, basically. That'll just be m to the power of 5. So we have plus n to the power of 5. And we have minus times minus. So that would be plus 1. Okay. So basically, we have this. Okay. So we have C divides this. And we earlier had, of course, from the GCD statement, okay, we have C divides m to the power of 5, n to the power of 5. Okay. So this implies that C divides the GCD of these two numbers. So okay? But this is equals to AB, okay? So basically C divides AB. So that implies that C is equals to AB. And we are done for this video. So that was quite a mouthful. There might be a more elegant solution, of course. I wasn't the one who proposed this problem. I proposed some other problems on the contest, but not this one. So probably the person who proposes might have a more elegant solution. But I hope you enjoyed this video and you learned some important and interesting facts about GCDs. So that'll be all for this video. Don't forget to like, share, comment, and subscribe, and see you in the next video. Goodbye. Cheers.